Hello and welcome again to my Physics Online video lecture series. In today's video, we're going to be exploring Newton's law of universal gravitation. This is the Newtonian synthesis of several things that we've discovered over the course of the semester, several laws and principles that we've discussed. And so we may begin by recalling a few of those laws and principles. The first one that we want to recall is that uniform circular motion requires acceleration. Specifically, if we have an object which is moving at a constant speed around a circle, that speed will be tangential, then the centripetal acceleration has to be that speed squared divided by the radius that the object is moving about. Our second thing that we need to recall is Newton's laws in general, and in particular Newton's second law, which essentially says that the sum of forces acting on the object should be the object's mass times its acceleration. It really is the rate change of the linear momentum, but we don't have any changing masses here, so we can just write it in the familiar form this way. And more importantly, that this law implies that there must be some centripetal force that is equal to the object's mass times its centripetal acceleration. The third thing to recall is Kepler's laws. So Kepler's laws, and specifically the third law, which we previously rendered just as t squared over r cubed is constant, but we could, we previously rendered it as t squared over r cubed for one planet is t squared over r cubed for another, but we could just render it as t squared over r cubed equals k, where k is some constant. So k just has some constant value for our system. And that value may change depending upon the system you're looking at, but it fundamentally is constant within a given system. So these three things can be put together to essentially arrive at Newton's law for universal gravitation, or most of Newton's law of universal gravitation. Okay, there's one other fact that we can get to, which is that if we want to know what the period is, so period of motion t can be found from size of the circle and from speed of the object. Period t is given by 2 pi divided by omega, the angular frequency. In some sense, that's how omega could be defined, but it's that omega is also the essentially rotational speed or angular speed. And so omega is v over r, so t must be 2 pi r over v. Put differently, you could think of this as saying that the time to complete the trek all the way around a circular orbit should be 2 pi times the radius of the circle. In other words, it's the circumference that's being described here. That divided by the speed at which the thing is traveling. So this is just another way of saying that speed is distance over time, and therefore time is distance over speed. Okay, so now we can put this together with these three things that we've recalled and obtain something that looks like the Newtonian synthesis. Okay, we'll start with the centripetal acceleration v squared over r, and then what we want to do is use that AC is v squared over r, and then essentially make the substitution from up here by noting that we can multiply both sides by v and divide both sides by t, and so you end up with v is equal to 2 times pi times r divided by the period t. So that means that this one right here, when we've made that substitution, is going to give us 2 times pi times r quantity squared divided by t squared times r. And so when you've multiplied everything out and kind of canceled like terms, simplified it, in other words, you end up with 4 pi squared r divided by t squared. Okay, now we come to Kepler's law. T squared over r cubed is k. So since t squared over r cubed is equal to k, we can also write that t squared is equal to that constant k times r cubed. It follows that the centripetal acceleration must be 4 pi squared times r divided by k times r cubed, or in other words, it's 4 pi squared over k times r squared. All right, now we actually want to go to Newton's law, Newton's second law. Fc is m times ac. So Fc is m times ac. That's m times 4 pi squared divided by r squared times k. And the Newtonian synthesis now comes into play by saying, well, where does that force come from? And the answer is it comes from gravitation from, let's say, the sun acting on the planet, or from the planet acting on a satellite around the planet, etc. So in some sense, this right here must be equal to that force of gravity, because that's the only thing that's present to supply a centripetal force. And the Newtonian synthesis basically says that this constant k is actually 4 pi squared divided by the mass of the attractor, the sun, if you're looking at the solar system, the Earth if you're looking at the moon and other satellites around the Earth, etc., times some constant that we call the universal gravitational constant. So when you put everything together, what you end up getting is that the force of gravity on a large scale, and maybe we should actually use a capital G here instead of a lowercase g, just to distinguish it from free fall acceleration. Our capital we'll use a subscript of capital G here to distinguish it from free fall acceleration near a planet's surface. And so when you make this substitution for k, what you end up getting is that the force of gravity is g, big G, times the mass of the attracting object, which I'm going to relabel as m1, times the mass of the other object, which I'm going to relabel as m2, divided by r squared. And so I'm going to actually come back up here and make note that this is essentially mass 2, this is essentially mass 1. And I've made that little change because this is true not only for large things like planets and stars and so on, but smaller things like even like individual people have some gravitational attraction between them. I also wanted to generalize it a little bit because this massive attractor, massive thing orbiting the attractor doesn't quite satisfy very well if you have like a binary system where both have the same mass. And it's also worth noting that via Newton's third law, the same force is applied back on the attractor from the thing that's orbiting it. The value of this constant g, this is the universal gravitation constant, it's approximately 6.674 times 10 to the minus 11, and the units for that are Newton meters squared per kilogram squared. And that's the Newtonian synthesis. Now, you could read up on history a little bit about, did Newton actually come up with the correct value for capital G and so on. Originally there were some terrestrial experiments, one called the Cavendish experiment. And essentially the way that worked is that Cavendish was able to measure the value of G. So this measured g using known masses. And those known masses, basically he had a set of very, very large balls like this, and they were connected to a suspension system that could twist around like this, and then he had an even larger set of bigger balls that could be attractors for this small set. And so essentially these would twist, and that would put a little bit of a twisting tension, a torque essentially, in this rope. And so he'd find what's the equilibrium position as a function of how far these initially began from the larger balls. And as a result, he was able to then make a plot, and from that plot get a value of big G. So this was a measurement or a determination of the value of big G. From here, essentially we've since had other things like satellites in orbit that have been able to detect what their attraction to each other are and basically add more precision to G. And that has essentially means that G is pretty well established at this point. The other thing is that now that we know what G is, we can figure out things like what is the mass of extraterrestrial objects or even of the Earth by going back through this Newtonian synthesis and kind of working it in reverse to get how the period is related to the distance but also to the mass of the object. Remember that in this Kepler's law, t squared over r cubed is just some constant. That constant has in it the mass of the attracting object. For our example, let's consider the gravitational force between the Earth and the Moon. So to determine the gravitational force, we need the gravitational constant, the mass of the Earth, the mass of the Moon, and the mean distance between the two of them squared. So this comes out to 6.674 times 10 to the negative 11th times 5.97 times 10 to the 24 kilograms times 7.35 times 10 to the 22 kilograms, all divided by 3.84 times 10 to the 8th meters quantity squared. And so this force of gravity between these two is, if you put all that into a calculator, about 1.99 times 10 to the 19th newtons. So that is your rough force of gravity between Earth and Moon. The period squared divided by the distance cubed, which is equal to k, is just 4 pi squared divided by g times mass of whatever object is being orbited. And so that means that now that we know a value for big G, we can get the mass of things like the Sun or Jupiter, etc. So maybe one more little note, which is that Newton's law worked out very, very well. It makes some very nice predictions, but it has its limitations. It starts to break down a little bit when you go onto quantum scales, where forces tend to be less important, and it's really energy and Hamiltonian and Schrödinger evolution that we start caring about. It also tends to break down for very, very massive objects. So if you have a black hole, for example, you get enough gravity that even light will kind of bend around it or fall into. So for a black hole, there's a feature called the Schwarzschild radius. So the Schwarzschild radius is the radius below which, if you have light passing near the black hole, it cannot escape. So Schwarzschild radius is like, in some sense, the radius that defines your event horizon. Anything closer to the black hole than that should not be able to escape from the black hole's gravitational pull, and so any information being carried, light, whatever, is lost to the black hole. And the Schwarzschild radius is actually given by 2 times the gravitational constant times the mass of the black hole divided by the speed of light in vacuum squared. And so again, c to 3 sig figs is 3 times 10 to the 8 meters per second. All right, as an example for the Schwarzschild radius, we might ask, if the Earth collapsed to become a black hole, what would be its Schwarzschild radius? And what about for the Sun? So we use the Schwarzschild radius of the Earth, and what we would do is 2 times g times mass of the Earth divided by c squared. And so that's 2 times 6.674 times 10 to the negative 11 Newton meters squared per kilogram times 5.97 times 10 to the 24 kilograms divided by c squared, which is 3.00 times 10 to the 8 meters per second squared. This gives us a Schwarzschild radius for the Earth of about 8.85 times 10 to the negative third meters. So this is just under 1 centimeter. It's a very, very small black hole. It'd be like smaller than this little piece of paper here. What about for the Sun, though? So the Schwarzschild radius for the Sun is 2g times mass of Sun divided by c squared. So you'd have 2 times 6.674 times 10 to the negative 11 Newton meters squared per kilogram squared times 1.99 times 10 to the 30th kilograms, all divided by 3.00 times 10 to the 8th meters per second squared. That gives us a Schwarzschild radius for the Sun of about 2.95 times 10 to the 3 meters, or in other words, just under 3 kilometers or just under 2 miles. So that is your Schwarzschild radius for the Sun. That may seem like a very large object, but from an astronomical perspective, that's actually quite a small object. If you think about how big the Earth is right now, its radius is about 6 times 10 to the 6 meters, and so that is, roughly 2,000 times bigger as a radius than the Schwarzschild radius of the Sun, and it's maybe 9 orders of magnitude larger than the Schwarzschild radius of the Earth. So black holes are very small objects in the sense of how much space their Schwarzschild radius takes up, but they are extremely large in the sense of how massive they are. In fact, neither the Sun nor the Earth should naturally collapse to form a black hole. You usually need something that has maybe 5 or 6 times the mass of the Sun to undergo a natural collapse into a relatively small black hole. So that's all for today's video. I hope you learned something from it. Hope you found something interesting in it. Thanks for watching.